think it's a good time to get started, so we don't run too late. It is a pleasure for me to present Matthew Mazloff. He got a BS in physics from University of Vermont, and then later on did a PhD at the joint MIT HUI program. But he's currently I think associate researcher, if that's the right word, at Scripps Institute of Oceanography, so just down the road. Wherever I go these days, I feel like Matt's name pop up everywhere. He works on a super interesting and important topic of how to link sort of very a dense set of observations with models to provide what is called a state estimate. And I'm sure we're gonna hear a lot more about that, and particularly a state estimate of the Southern Ocean, where he's involved with the SOCOM project, which is a big effort to understand the oceanography of the Southern Ocean. And I think the rapid expansion of data from autonomous platforms like Argo just makes Matt's approach super important and relevant for both understanding sort of ocean processes, but also for getting to the baselines and estimates for which to compare changes, and especially observed changes. And some of you may remember Lynn Talley came and gave a presentation. Might actually been the last in-person presentation we had in ESS nearly 2 years ago. And there we saw sort of some of the applications of Matt's work that was brought up on multiple occasions during her talk. Anyway, it is a pleasure for me to introduce Matt, and both here today virtually, and then we hope that in the near future we can invite him in person and have sort of some longer conversations. So Matt, thank you for coming, and we look forward to hear your talk.
Thank you for that nice introduction. Thanks for the invite to be here today. I took this as an opportunity to, given that the audience is kind of wide range in Earth systems, to talk in general about the Southern Ocean. And I'm going to focus mostly on the physical oceanography today of the Southern Ocean, and really get into how the ocean, I'm going to talk about the momentum budget and the heat budget and the freshwater budget and the carbon budget of the Southern Ocean, and how it all works together. And this is basically a talk that I haven't given in a few years, and so I'm kind of excited to dig it up, because it really is kind of fundamental to what I did for my PhD and after as well. Lately, I've been doing a lot of other things, and but I'm not really going to go into that much today. So what I'm going to talk about is the Southern Ocean energetics and Southern Ocean budgets. And I'll start off with a very brief introduction of the tool, and that is the a state estimate. And I'm not going to talk much about it, but I do want to mention the difference between kind of what a state estimate is and why we're doing what we're doing. I think many people are familiar with reanalyses, whether there's ERA interim or ERA 5 or NCEP or NCAR or JRA. There's lots of reanalysis where the software is the same. It's the same as doing weather forecasting. But when there's data coming in all the time, and here we're talking about ocean data, it's coming in all the time, and you can run your model and you can adjust it towards the data at some interval. And for many methods, many applications, you just want to bring it to the data, and you want it to control the solution as much as possible. And that's what reanalyses are. They're built off weather forecasting systems. And what happens is when the data comes in, there's some simulation interval. Maybe it's a day, maybe it's 8 days. You're going to adjust the solution towards the data. Well, that gives you a solution that looks very nice, right? You have a lot of control of the solution. You can fit the mesoscale features, the eddies, but you are breaking the dynamical budgets all the time. So when we really extend that window out as far as we can, we refer to that as state estimation. And some of our state estimates are, depending on if we really want to fit the mesoscale features, maybe the window is only 60 days, but that's still a lot shorter than 8 days. We'll have a lot of physics in the model manifesting. for this Southern Ocean application, we really went extreme and said, we're gonna lose some control of the solution. We're not gonna fit all the eddies at the right time, in the right place. But we want to adjust the solution over, well, we did 3-year windows, and do the best we can to get the background state as close as we can. We're not going to look as good as if we adjusted every, say, 1 month, but we're going to have a solution with closed dynamical budgets. And the reason why we did that is because if you go and take, I'll give you one example here. If you go and take there's a lot on this page, but let's just look at this one where my cursor is right here. This is the, oh, I'm sorry, where my cursor is right. This is the ORS4. This is the ECMWF's ocean reanalysis product. They're now on ORA S5, but the ORA S4. And the blue shows the diagnosed heat flux, the heat coming out of the ocean. And the green shows the total ocean heat gain. And then the orange is what was done through the adjustments. And so there's more heat gain in the ocean. There's basically way more heat going out of the ocean than the change in the ocean heat content. So it's hard to do attributions when something like that happens. And just for more perspective, here's their ERA interim, their atmospheric reanalysis and the heat gain, and that's inconsistent with the ocean heat content change as well. So there are these balances between conserved budgets and controllability of the solution. And for this Southern Ocean application, we really want to understand the budgets. And that's because the Southern Ocean budgets were not well understood. To argue they're still not well understood. And so what I'm going to focus on today is what those budgets are. I'll just mention that this is the ECHO, you may have heard of it, ECHO software. The main ECHO project right now is at JPL, although it started at Scripps. And like I said, we do regional state estimates. So we have California current ones, we have tropical Pacific ones, Northwest Pacifics, and Gulf of Mexico. But today I'll talk about the Southern Ocean state. Okay, so that's the tool, that's the methods, and the one I'm mostly analyzing today is this 2005-2010, which is available at sofc.ucsd.edu if anyone wants the solution, and all the budgets are on there. And if anyone has any questions, please interrupt, or I'll try to monitor the chat. You can raise your hand or anything. But I want to move on and talk about what we find when we do these state estimates. So this is a 6-year run. Like I said, it's 2 3-year simulation windows. And this is the horizontal circulation that we derive. So this is as consistent with all the Argo observations and satellite observations possible, with the caveat that because it's a 3-year window, we've lost a lot of controllability. And so there is some significant differences as well. Okay, so I'm not sure how familiar everyone is, but the main feature of the Southern Ocean is this incredibly strong Antarctic circumpolar current system that runs from west to east around Antarctica. So here's Antarctica down here, South America, Australia, Africa. Here's the Gulf current. So these are the subtropical gyres, Gulf current. The Indian is very energetic. Pacific subtropical gyre, the South Atlantic subtropical gyre. And then we have the Weddell gyre down here and the Ross gyre down here, and in between them is this Antarctic circumpolar current. And when people theorize about how the circulation in the Southern Ocean works, it's always gets complicated because there's no land boundary here. And for all the other gyres, people talk about sphericity balance and vorticity balance, and that's how they can talk. That's how they close budgets and figure out how things work. But because there's no land boundary here, the water flows all the way around. People get confused about what's going on. In particular, people talk a lot about the overturning circulation of the ocean and how it moves heat around and helps set the climate of the Earth. But the overturning circulation, when you step out of the Atlantic into the Southern Ocean, is a very complicated thing. And my goal of this talk is to explain how it works. So that's the point. And the reason why it's so complicated is because the budgets that it has to close, momentum, heat, they're not necessarily in compliance. They don't make it easy for the Southern Ocean. Okay, so people love to, and this is really the viewpoint from the 90s, early 2000s. People wanted to talk about the Southern Ocean in a zonally integrated way. They take this solution, this is how the horizontal circulation looks, but zonally integrate all the way across and look at how the overturning looks. And this is the picture you get where you have so this is an overturning stream function. You have incoming water from the subtropics coming in, and there's a split where some is deep water coming back out, some rises up to the surface and comes back out here. Well, there's a couple issues with this. The first issue is that if you talk to atmospheric scientists or climate scientists, the mindset, the mentality is that the ocean is bringing heat from the tropics to the Antarctic continent. And so that's what you're seeing here is the heat transport. And most of the total heat transport, most of the balance is held by the atmosphere. The ocean plays a role, and it does bring heat from the tropics to the Antarctica. Now, if you look at this picture, like I said, and this is the schematic from Kevin Spear et al. 2000, you see the surface waters are going equatorward. And this immediately raises the question, well, how can the surface waters go equatorward and the heat go poleward? The other problem with this is if you took we do have the coldest waters around Antarctica. If you just took all those cold waters and pushed them equatorward, you would overturn all the isopycnals, all the density surfaces. The ocean would be completely unstable, and you would see convective cells that went extremely deep. You have to say, well, how is this? Now, this picture that you see here, the fact that water is all going equatorward, that's because the wind's pushing it. That's the momentum budget. But how are we satisfying the heat budget? I guess if anyone wants to just yell answers out too, that's welcome as well. Okay, so we have this question. And the first thing to note, the other thing, when you first look at this picture, is that it looks like water is coming up from 4,000 meters all the way to the surface, all at 60 south. And that would be quite something if that was happening. And in fact, it's not happening. And so first we'll solve that mystery. The fact that water looks like it's coming from 4,000 meters to the surface is because we're looking at this overturning stream function in z-space. And the ocean doesn't live in z-space. We do. We like to talk about, oh, that building's 10 meters high, or we live in z-space. We live in gravity, everything's. But the ocean moves along neutral surfaces, moves on isopycnals, density surfaces. And when you think about what's happening here, and I've blown up the top 300 meters here, but what's happening here is the ocean is not moving in a zonal way. This ACC, which moves about 155 sphere drifts all the way around Antarctica constantly, moves poleward, then equatorward, and then back forward. So it spirals around. And it turns out that when it's moving poleward here, it's not so constrained by bathymetry mostly. So it's this big 5,000 meter deep slab of water. But when it moves equatorward here, and it does so much like a western boundary current, it's much shallower here. It's about 3,000 meters. And it's moving the same amount of water, so you can picture it would be accelerating. The whole thing is kind of leaning over, accelerating. And when it does that, it lifts up the isopycnals. So the neutral surfaces are now higher in the water column. And so if you were a water parcel traveling across the South Indian and South Pacific, and you moved into the South Atlantic, and you were at 150 meters depth, all of a sudden you kind of accelerate up and move to 100 meters depth. And so you do this kind of pattern. you do a small circle. And the one that started at 200 meters depth, well, that one went up to 150 meters depth. And the one that was at 300 meters, that one went up to 250. So the whole, as these water just goes around and around, it spirals up. Nothing is really changing in a thermodynamic way. There's nothing really happening. It's just spiraling around at different depths. But when you zonally integrate, and you can see what happens is it looks like one giant overturning cell. And this was labeled the Deacon cell. And people wondered for quite a while how we could have a Deacon cell. And it shouldn't be named the Deacon cell. I hear that he knew the answer to this, but he got labeled Deacon cell anyway. This paper, Spear and Rim Tool, they had this paper called the diabatic Deacon cell, and they explained what was actually happening here in the 2000s, and said that when you do the Southern Ocean overturning, you should not integrate on, on vertical levels. And I think that's a good lesson for pretty much the overturning circulation in general. If you care about the overturning of heat, then maybe you should integrate along temperature surfaces, or the overturning of carbon, maybe integrate on carbon surfaces. Here we're talking about volume, so we integrate on density surfaces, constant volume. And so now that we're on density surfaces, a couple things. One, the surface is now kind of angled because the water is getting denser as you go forward, and the surface layer circulation is it looks much different. It's not 30 sphere drifts right up close to the surface. In fact, it's actually going the other way right here. So there's much less of this strong surface circulation when you think of it in density space. This is also a stretched axis. Most of the water is relatively the same density compared to how much it changes right as you get near the surface. So that kind of explains why there's not so much upwelling, and we don't have so much issues with overturning and convection down to, say, 3,000 meters all over the Southern Ocean. It just doesn't do that. But it doesn't tell us still why how the warmest water goes forward. We still have between 60 and 35 south. We still do have a primarily equatorward flow. So we can look in this data estimate and say, well, does it actually have heat going towards the Antarctic? And the answer is yes, it does, and it's relatively consistent with this climate assessment, Sula and Trenberg, saying that about a half a petawatt or 0.4 petawatts is going from the tropics to the Antarctic. So that you can, what I plotted here is the heat transport, but you can just look at the red line. This is the total heat transport. And it does have structure, but basically heat is going from 25 south all the way to Antarctica, and the heat is being lost to the atmosphere as it goes. So we still have surface flow to the equator and heat to the Antarctic. And does anyone want to have a guess at or shout out why that is? Anyone know? Well, part of the answer is the freshwater transport. That really we were showing them the most buoyant water is going equatorward. But that water is the most buoyant because it's very fresh. So if you look at the freshwater transport in the model, you see that it is the strong, about a spare drip of fresh water coming from Antarctica to the tropics. And so we've looked at the freshwater budget, and what you see is that there's this huge, this is not just rain, there's this huge freshwater cycle that's quite fascinating in the Southern Ocean. And so first let's look at atmosphere and land. And you see there, it does rain or snow over the Antarctic circumpolar current, but there's also a lot of fresh water coming in from the Antarctic continent. So when you talk to glaciologists, they're all worried about the melt for a sea surface height, but it also has this really big impact on what's going on with the overturning circulation. And so through very complex relationships, it is also setting the climate in that way and changing the carbon budget as well. And we'll get into that later. But what happens is it's really a very strongly related to the sea ice dynamics, that the fresh water comes off the continent, very strong winds coming off the continent, katabatics, and all this ice, the Antarctic it's really got ice factories. All this ice forms right around the continent and it gets blown off. So even though we have ice all the way out, doubling the size of the continent, most of that ice is formed right near the continent in these coastal polynyas, and they form ice, wind blows them out, open water, form ice, wind blows them out. So you get very salty water around the continent, that deep shelf, or the dense, high salinity shelf water. And the circumpolar deep water, the deep water that's upwelling, mixes with that, and that's how you get Antarctic bottom water, which is the densest water on Earth. And that's that bottom cell. But if you think about the top cell, which is what's bringing the warm water to the Antarctic, now how does that work? Well, it's coming up and it's getting freshened by all this. This is the total, by all this ice redistribution and also by some precipitation. And so we do have equatorward flow, and there is buoyancy loss from salt. But when they're talking about buoyancy loss in this picture, that's mostly from the fresh water, right? The buoyancy loss causing Antarctic bottom water, buoyancy gain from fresh water melting ice, basically. So it's very seasonal, and that pushes into the equator. So that because it's gaining buoyancy as this water comes up, goes equatorward, it's not overturning all the isopycnals, and it's closing both the momentum budget and the buoyancy budget, thanks to the fresh water. So to pause for a minute and talk about what we've talked about so far, hopefully learned so far, is there is very strong equine transport. There's incredibly strong winds, and we have 30 spherogyps of water, which is as strong as the mean transport of many western boundary currents. Huge amounts of surface water being blown essentially towards the equator, and that's carrying fresh cold water towards the equator and achieving stability. So really we have this exchange of water, and that's the next part, is how does this exchange work? We have this exchange of waters where we have these fresh waters moving equatorward and warm waters moving poleward. And so again, this 2D schematic that we like to look at doesn't allow, because it's 2D, for this kind of 3D exchange. What we really want to know is, how does water go this way and bring fresh water, but how does it go this way and bring heat? So that's the next part of the talk. And because we have a model, we have movies. So I like to show movies and just to emphasize how complicated the whole thing is, and how these zonal pictures and simplified pictures of the budgets, well, they can be nice, and I do make them myself. They're not always useful because it's a very three-dimensional, time-varying system that you need to take into account. So we want to know, how does the heat budget close? We know that the water is moving equatorward, it's buoyant, but we still need to get heat towards Antarctica. And basically, even though this looks crazy, this is the heat flux, we need to bring heat to the atmosphere right near Antarctica. Well, we can look at the heat budget, and I'll try to keep this as simple as possible. We have a lot of terms in the heat budget, and this is, we don't have to look at all of them, but here's the air-sea flux. And it has very complicated structures. It's not at all well represented by 2D picture. However, when you look at, so this is very reflective of the SST. I don't have the SST here, but I have the SST plotted here, but I've taken out the meridional, the average SST in latitude. So this is just the residual in longitude of the SST, and you immediately notice that the SST is much colder in the Atlantic and Indian section than it is in the Pacific. We have really warm SSTs in the Pacific. So there's this strong zonal asymmetry, which is hinting at some kind of exchange, some kind of asymmetry that may allow waters to move in different directions. And when we look at the budget in these basins, so this is the budget in the Atlantic and the Indian, and what you see is there's a lot of air-sea flux. So the atmosphere is the ocean's gaining a lot of heat from the atmosphere. The cyan line, cyan bar, that's the Ekman. That's the cold water being blown from Antarctica northward into the ACC. And you see that's about the same in these. There's the same amount of cold water being blown north in both domains, but the difference, the asymmetry, is that the ocean is gaining heat from geostrophic advection, basically the ocean circulation in the Pacific, and it's gaining heat by air-sea flux in the Atlantic and Indian. And while I said I don't like schematics, I think they're not very helpful. I think this is a helpful way to summarize it. What's happening is, think of the ACC, so it's contoured here, and if we think of it kind of as a spiral, as I started to allude to earlier, it comes north and it mixes and it gains a lot of heat as it comes north in the Malvinas Current. It's bringing cold water from down here up, and it's just gaining a ton of heat from the atmosphere. It continues to gain a ton of heat from the atmosphere. It runs in the Brazil-Malvinas Current, which is Brazil Current, which is very warm, but surprisingly, it doesn't pick up a huge amount of heat from that. It does pick up heat from it, but it does pick up a lot of heat around Kerguelen when the Agulhas Current comes down from the subtropics and crashes into the ACC here. That picks up a lot of heat. And then it picks up a lot of heat here as well. The East Australian Current comes down. So in these regions, it's picking up heat from the atmosphere. And then it crosses this Campbell Plateau, Macquarie Ridge, and it moves poleward, just flows poleward. You know, there's a Indo-Pacific rise here, but it's relatively free. It just moves poleward. And because it's picked up all this heat, it now starts to lose it. If you think of this line of constant longitude, it's brought this heat from 40 south to 65 south, and it's going to lose its heat here. So we have this large, just conveyor belt, essentially, of constant heat uptake by the atmosphere and released by the ocean. Now, maybe this sounds like a detail, but you hear a lot about there not being a mean geostrophic. In the oceanographic literature, you hear so much about there being no mean geostrophic transport across Drake Passage, because you can't you can't have geostrophy, PDX, zonal gradients, and you can't have a zonal gradient. Pressure is continuous all the way around. So people often say, oh, the ACC can't bring heat poleward. But really, that's true. It can't bring mass poleward, but it can bring heat. It's bringing heat. It's bringing warm waters poleward here, and it's conserving mass, moving back northward with much colder waters. So where we're at is we have this exchange of, well, we still haven't figured out the exchange completely, because but yes, there are warm, salty waters coming down from the tropics and the subtropics, and there's cold, and it's picking up, it's mixing with sea ice melt, getting a lot fresher, getting a lot colder, and coming back north. So we have this exchange of warm, salty waters moving poleward and cold, fresh waters moving equatorward. So we wrote this up about the heat budget. We kind of figured that's how it worked. but turns out there's more to the story. When you look in detail about the momentum budget and how this exchange works, you start to realize how it's all very connected. All three of these heat constraints, freshwater constraints, momentum constraints. And what it comes down to is, if you only had momentum constraints, the atmosphere would push on the water, and the water would just push on the land, and that's how momentum would just flow through the system. But to do that, it would rely on equatorward flow at the surface, that Ekman transport we talked about, and a return geostrophic flow. And to get away from that, water ends up pushing on water itself and exchanging. And I want to try to explain that. I can probably skip that. Okay, so the mean momentum input, I'm gonna skip the move. I think I'll skip the move, show a little bit of it, but it's also very complicated. But it is large scale, and it's relatively this time mean wind stress input. So you look at the time mean wind stress input, you have there's more momentum going in some places than others, but it's pretty uniform. That's the source of momentum to the Southern Ocean. If you look at the sink of momentum to the Southern Ocean, it's very complicated. The blue's balancing it, and what you see is actually most of the momentum is leaving on South America. A lot is also this Macquarie Ridge, Campbell Plateau, and Kerguelen. So the sources and sinks are very spread out, and the momentum travels through the water to get there. But when it does that, this is how Jess Macy diagnosed it. Basically, when you want to look at these sources of sinks, you look at the pressure on the east side and the west side, and you can see that this is called bottom form drag. So bottom form drag is across land, and that's the sink of momentum. It actually affects the rotation of the Earth, because if you're storing momentum or not, the ocean is such a large mass that it can change the rotation a bit. But what's important to note here is that you just have this pressure difference across land, and you're basically putting momentum from the water into the land. But you can also do this, you can think of the same picture where this is not land, this black, but a different water mass, different density class, say. So that one body of water is putting its momentum into another body of water by having a strong pressure gradient against it. And that's known as interfacial form stress. So if we look at a specific density class, so this is 28.2, this would pretty much be considered, everything below it would be considered Antarctic bottom water. You can, if someone has a comment, please interrupt me. You can see Antarctic bottom water is putting a lot of momentum into the land, but there's also places where it's got, it has these kind of contours that are surrounded by water, where water, lighter water, could put its momentum into the Antarctic bottom water and force it to flow by geostrophy. So we've been talking a lot about the overturning stream function, but you can look at this in terms of a transport as well. So the overturning stream function is the integral of the transport. This is just the transport in each layer. And so again, you have circumpolar deep water coming forward, and bottom water going equatorward, circumpolar deep water going forward, and surface water going equatorward. And if you break this up into what's balancing these terms, so what is the fundamental balance? There's really two terms. There is Ekman, the wind is basically pushing this. There's some viscous stuff down here, but basically the ocean is in geostrophic balance, except for the surface where there's winds blowing. This is large scale, and the winds are blowing and forcing all this water equatorward. This is that Ekman cell we were looking at. Meanwhile, down below, it's in geostrophic balance, and if there was no buoyancy constraints or anything like that, we would probably just conserve mass by going forward like this, and we could just upwell like the Deakin cell shows, and because we wouldn't care about buoyancy, and return flow. And that would just be this balance of bottom form stress or pushing on land, balancing wind. There would be a two-term balance, and it'll be very simple to understand, and we'd like it. But there is a third term in there, and that is that third term. Some people call it eddy term. It's an interfacial form stress, basically water pushing on water, allows the ocean to not have a simple two-term balance, to have a three-term balance and redistribute the momentum, move the water the way it needs to move water to close the other budgets. And so what you see happens is the interfacial form stress, where there doesn't need to be land, it's water pushing on land, on water, can be quite large and drives a forward flow that really slows down the upwind flow at the same density classes. And there's some pushing on land too. This is mostly around Antarctica, South America. So this is pushing on land too. So now that we have this three-term balance, we can look at where the interfacial form stress is happening, where water is pushing on the water, where it's exchanging, to see really where there's a lot of exchange between that cold, fresh, and warm salty. And so we split it up into kind of a surface layer, intermediate layer, and we plot it. And this is, we're getting near the end of the kind of, hopefully not too confusing stuff, but this is kind of the take-home message, is that even though it seems like there's just this big conveyor belt that's driving, that's bringing waters around Antarctica, and that does have a huge role in the heat budget, what's really important for closing these these buoyancy budgets is exchange over right at certain topographic hotspots. And so what you see is, right, we have this large amount of light water pushing and moving, so blue means move polar, large amount of light water moving poleward. That's not balanced by anything except pushing on denser water that's moving equatorward. And so cold, fresh water likes to leak out of the Ross Sea here and moves equatorward and is balanced by leaning on warm, salty water moving back equatorward, moving back poleward. And that is closing the budget. It's bringing that heat poleward. And what we used to say is all, like, we used to think of the ACC as kind of a zonal jet, and it would go unstable, and that would flux buoyancy poleward. This is much different than that. It does have to do with eddies, and the variability of it is driven by barometric instability, but it's very much a mean flow that is just two strong currents pushing on each other in the middle of the open ocean. It happens again over Macquarie Ridge, around Kerguelen, where there's just these really strong meanders, really complex flows, but it does have this exchange of buoyancy, of warm, salty, cold, fresh, that even though the momentum budget just wants to blow that surface water equatorward, allows other budgets to be closed. What's important about all this from a climate perspective is that this budget, this third term in the budget, really allows you to decouple things like wind stress from overturning circulation, because you can crank up the wind stress and you could crank up the overturning circulation, or you could just crank up this interfacial form stress stuff and not change the buoyancy budget at all. So how the ocean responds to changing and forcing is non-trivial. It's a three-term balance, and nothing's linear about it. So all that, okay, so I have one more point to make before we move on to questions, and that's the carbon budget. But first we'll just summarize that that when it comes down to it, the momentum budget is air pushes on land, but it's not direct. It's air pushes on the water, and the water pushes on the land. And in between that, the water can push on water and completely change the overturning circulation and the strength of it. And so when people theorize about how the overturning circulation is set, there's no direct. I wish there was an elegant equation for how strong the ACC is. I wish there's an elegant equation for how strong the overturning circulation in the Southern Ocean is, but there's no direct relationship. It's got this eddy term in between. Okay, so while the momentum budget was complex, the carbon budget's even worse. And this is the carbon flux in the state estimate. There's a lot going on here. Again, you saw in the heat budget, there's a huge seasonal cycle. Here, there's a huge seasonal cycle too. Blue means in the ocean's taking up carbon, and when it in the winter it cools down, it takes up carbon. In the summer, it off gases carbon. So you see that. You also see that the sea ice insulates the carbon flux, so there's less flux of carbon under the sea ice. Upwelling of carbon-rich waters happens all around Antarctica, and it has the pattern of ocean circulation. So you see a lot of the frontal structure, the upwelling locations. But of course, we also have biology. So like around, even though this is summer now, outgassing, austral summer, you see there's a huge carbon uptake around Tasmania due to biology, and you can see the biology and the nutrients leaking off New Zealand and bringing waters in. You see the flashing is the piston velocity changing, basically the storm track. When it flashes white, there's no winds, there's not a weak carbon flux. PCO2 changes relatively slowly in the ocean, and so it's really modulated by the wind. So when there's bright colors, that's the storms coming through, churning up the water and releasing carbon. So the carbon budget, I don't think I have the mean flux. The mean flux is much smaller than this. It's a small residual right there. I think this is my last results slide. But the carbon budget, while I've been saying the meridional overturning is so complicated and it's complicated balances of small scale exchanges, you see the overturning circulation in the carbon budget. So first, this is the total dissolved inorganic carbon transport by the ocean in the upper 650 meters. And it's red here and blue here. What's happening is vertical velocity is bringing carbon up all around Antarctica. This is the overturning circulation. It's bringing carbon up all around Antarctica. This is on average red, and when combined with the other terms, like horizontal, you get this nice clean red smooth pattern. It then makes it near the surface. This is the Aegis-Shark. This is the Ekman transport. You can see where the Ekman transport happens. It carries this upwelled carbon equatorward, but then it subducts in the mode waters and the subduction zones, and so you see this upwelled carbon moving out and then moving back down. So the overturning very well manifests itself in the carbon budget. And what's so important then is, even though we don't have a nice elegant formula for what sets the strength of the overturning circulation, it is setting how fast carbon is being pulled. Deep, very high carbon water is being pulled up, that carbon is being released to the atmosphere, and then again how fast it's subducting and taking with it anthropogenic carbon. So we do need to understand the overturning, and from a carbon point of view, it does look much more like a 2D budget, but we're still working on understanding the carbon budget more. So so the wind stress inputs momentum, bottom form stress removes momentum, but interfacial form stress, water basically just pushing on water and causing one water mass to go north, the other to go south, redistributes the momentum, allowing buoyancy constraints to be satisfied and setting the overturning strength. The overturning strength then regulates carbon and nutrients distribution. And buoyancy constraints and carbon fluxes are both very sensitive to sea ice cover. I didn't go into that much, but you can kind of see it from the movie that both the wind stress, heat exchange, carbon exchange, there's some very strong gradients between the atmosphere and ocean in the austral winter, and that's insulated by sea ice. But the sea ice is changing a lot. This is a relatively old slide, and it's changing even more now, but you can see the duration of the ice season is changing a lot. And then this, in 2017 and 2018, a big news event was in the middle of the winter. So this is September 25th, a large polynya opened in the Weddell Sea. And that can have devastating effects for carbon, heat, and freshwater exchanges. It's since closed, but there's a good chance the overturn is going to change quite a bit in the future. And I'll stop there and take questions. Thank you.
Thank you, Matt. That was awesome. Are there any questions for Matt? You can either post them in the chat or say them out loud.
Ask a question?
Go ahead.
Do you think it's useful to think of for the heat transport, like the atmospheric scientists think of stationary waves, and that picture you have of the ACC flowing south and back up, it looks like what atmospheric science would call a stationary wave, and you can do your budget, your zonal budget, by including the contribution of the stationary waves. Is that something you thought about, or is that useful? Or
it is, and that's, we have done. You're right. It's stationary waves. When I was doing my PhD, everyone talked about the transient eddies bringing the heat forward, and that was the answer to the problem. And then we realized since then that it's much more the stationary waves. I think the big question's still out, and I kind of had I didn't answer it, but I kind of maybe made an opinion about it, is whether those stationary waves are the full AC, what are the length scale that we should call these stationary eddies, these stationary waves? Is it the full ACC conveyor belt, or is it these, I guess you can see it in here better. So we have this full ACC bringing water from 60 south to 45 south, back to 60 south. Is that the main mechanism of bringing heat, versus every time you have one of these little stationary waves where you're only going 1 degree of latitude, but you're taking water that was experiencing relatively cold atmospheric conditions, and you're moving it a degree north and back south. So you have all these little wiggles. And if we could, and I don't think anyone's done this yet, if we could separate basically bandpass the stationary waves and say, well, what is the most important thing for getting the heat? There is the transients, and that's important too, but the fact that you're constantly bringing up a parcel of cold water equatorward, back poleward, equatorward, back poleward, and it's going to lose a little bit of heat each time. Is that the most important thing? Or for this net transport, almost like the Deacon cell where it all adds up because all these little wiggles, or is it this big thing? But yes, it's very much the same. It's stationary waves. And the transient part, we used to think of it just as a zonal jet, where the ice signals would break, and they would go barricade unstable, and you'd have a transport. But it's what we were finding is that it's really the eddies wiggling these stationary meanders. So they're not so stationary, but you have the stationary meander, and then the eddies act on part of it, just kind of basically flexing it, and that ends up causing a lot of heat transport. And that's where so when you have a big eddy field, it may actually not be important for heat transport, but the big eddy field on either upstream or downstream of one of these big stationary meanders really can end up making a big difference.
Keith, you had a question?
You mentioned the the interfacial stress sets the north-south flows, which sets the overturning. Could you expand on that a little? So you mean the
Right.
overturning of the upper cell is what you mean there? And
well, actually,
you know,
both.
like-
I guess I never wrote the equation down, but the
even just qualitatively, how are they related? Is it tied to the speed of the two water masses, the density difference of those two, the momentum passed, or
I guess I'm having a little trouble parsing the question, but I think I know what you mean. I hope I get this. If you just think about conserving momentum, when the wind blows, it blows mass equatorward. And now we have to, so we're done. We've closed momentum. But now we have to close mass budget, so that water has to come south. The easiest thing to do would be for it to just lean up against land and come south as kind of a boundary current. And we'd call, since it's leaning against land, we call that bottom form stress. If you didn't have to worry about anything else, you'd probably just stop there. But really, so this term is wind stress input, and this term is land output. And then there's a third term in the momentum budget that is the eddy term, the stationary wave term. And that can allow you to, where you have places where, say, you want to bring, the ocean wants to, this is Drake Passage here, there's no land right here. The ocean maybe wants to conserve mass, or needs to conserve mass at that same location, so that it can close other budgets. There's no land there, and so the only way it can do that is through this eddy term, where it ends up just taking, it has to conserve mass there. If you integrated these transports, the ageostrophic would integrate to about 30, and the barotropic and the bottom form stress would integrate to about 30. So it'd be 30 going north through ageostrophic, 30 coming south through geostrophic against land. And the interfacial form stress would integrate to 0. There's no momentum sinks within the ocean itself. Energy can be sunk within the ocean, but momentum is conserved within the ocean. The water parcel can't just dissipate momentum, but it can pass that momentum to another water parcel. So you could almost think of it as like two trains on tracks next to each other, and one can push off the other or push the other one. And so these two trains, they have no way of throwing away momentum, but by one pushing on another, one can go one way and the other can go the other way. This is what the interfacial form stress is. It's basically two parcels of water saying, I have to conserve momentum, but I want to bring this cold water, this fresh water equatorward, and I want to bring this warm water poleward, so we'll just push on each other. And so by doing that, they can actually completely shut off the overturning circulation, because they could in say temperature or in buoyancy, because they could close all the budgets right at the surface, all the other budgets. I don't know if that helps.
but they don't. Right.
Well, they do in a lot of way, in the sense that the in density space, you see less than 30 spare drips of the lightest water going north, and in temperature space, you would actually see the water going south, even though the mean the mass transport if you did it in Z space, the top 50 meters of water or 80 meters of water are all going north. If you integrate it in temperature space, you'd actually see the warmest waters are going south. And so that difference is just because the ocean preferentially took, I shouldn't anthropomorphize, but the ocean preferentially took warm water and warm salty water and cold fresh water, and exchanged them in such a way that in temperature space, it looks like the warmest waters are going towards the Antarctic continent.
Jim, you had a question?
Sure. A really interesting talk. My question is about future changes in circulation. I guess with climate warming, we expect more water vapor transport in the atmosphere to Antarctica, potentially a greater freshwater flux. What's your sense of, in terms of changing future circulation and the importance of like changing freshwater inputs, potentially an acceleration of freshening from Antarctica versus versus changes like in the wind stress or like, changes in the westerlies position?
Yeah, I'll have to think about that a bit, but yes, so you'd expect if you're adding more fresh water, that if you just have the idea that really the buoyancy constraints, the reason why we have to have this kind of complicated balance and we have to have eddies and meanders is because where's that slide? This, is because when you have water going equatorward, it's not stable. Adding more fresh water stabilizes it and makes it easier to have a stronger overturning circulation. I would think that basically more of that, you'd need less interfacial form stress. You would need less eddies by dumping water where you're bringing that water forward. It's hard to say.
Thank you.
Especially the understanding of the physical oceanography of the southern.
Well, that's the biggest the biggest conversation of the SOCOM project right now is that the SOCOM project put biogeochemical Argo floats in the Southern Ocean, and for the first time, we really have extensive measurements of pH in the Southern Ocean in the winter. And when you, if you just infer carbon flux, well, you infer PCO2 and then infer carbon flux from these floats, it shows a lot more carbon coming out of the ocean than we previously had thought. And so either we underestimate the uncertainty in the budgets, or we're missing a sink somewhere, or there's something wrong with the fleet of SOCOM floats. But this is a really active area of research, is what's going on, because it looks like the ocean is putting a lot more carbon into the atmosphere than we had previously thought. If you ask me, I think it's just, it's all within the uncertainty. But a lot of people totally disagree with that and say that we need to understand what's going on, because that's too much carbon. That's too much carbon. We don't think that's within the uncertainty. So that's a whole nother that's a whole nother talk.
Well, that's obviously a big question in our mind here, but so we'll have to invite you again, right? Anyway.
I don't know if I'll be answered that anytime soon, but I mean, there's this new paper out. I think maybe Matt Long or Britt Stevens is the lead author, saying from atmospheric observations, there's a discrepancy. It looks like there's too much carbon is inferred from the floats, and so I think that's either the floats have an offset, or the inferences from them an offset, or it's, I mean, I do mapping kind of for a living, and so I think it's probably just all within the uncertainty, because people are extrapolating more than they probably should. But but I've been wrong many times, so let's see where it goes. I will one last thing. I noted, I just kind of off cuff said that maybe more fresh water make a stronger MOC, and that's kind of interesting, because on the in the North Atlantic, people say the opposite, but the Southern Ocean is very different than the North Atlantic, and it's not so much about convective instability, because you do have there's so much wind power going into the Southern Ocean that actually adding fresh water kind of makes it easier for the winds to pull up dense water, lightens it right away. And so it's kind of interesting. I hadn't thought of it.
Francois, you're next in line.
Okay, yeah, well, it's a bit of a self-serving question, but you pointed out that you can see the traditional picture of the overturning by looking at the carbon fluxes. And so would it be correct to say that the biogeochemical tracers have are particularly good for informing us about the mean state of the circulation, like the long-term averages? Is that a fair statement?
Yep, totally. I noticed there's a comment about it could also be uncertainty in the gas exchange parameterization, and I totally agree that that could be the issue too. I have done runs where I changed the gas exchange parameterization, and it was kind of surprisingly not as big an effect as I thought, but it's so uncertain, and maybe I didn't change it enough. Regarding your comment about the fact that the biogeochemical tracers show these features, when they have so much stronger vertical gradients in the biogeochemical properties that I think we can learn so much about the physics of the ocean from them. As soon as I started doing biogeochemical assimilation, I first started in California, and we had a state estimate there that I thought was just I was so proud of. Oh, it looks so much like the observations. And then we added, and that's partly because there was a lot of observations. It was, a place where you can do well. And so I thought this is a great state estimate. And then we add biogeochemistry, and off of San Francisco, there was crazy oxygen. And I realized we had this unphysical upwelling location. And it didn't show, the TNS it wasn't a big deal for temperature and salinity, but oxygen showed it. And I've really come to the hand wavy argument that the Argo floats, the satellites, the physical measurements, they really constrain the horizontal circulation really well. And if you only care about the horizontal circulation, then we don't really need biogeochemical measurements. But if you care about the vertical transport, throwing in things like oxygen or nutrients or carbon measurements really show you your model errors in the vertical circulation. And that projects not just on biogeochemistry, but obviously air-sea exchange of things like heat, because it is affecting the upper ocean heat content. So I really, I'm not a fan of how much it slows the models down, but I'm a huge fan with how well it shows you errors in your vertical transport. So I do appreciate the biogeochemical measurements for that.
We have a question from one of the junior people. Isabella, do you want to say your question? Sorry, not Villicona, another Isabella. I don't know if she's still on.
Yes, okay. I can give my question
now. Yeah.
That was a great talk, by the way, Matt. I really appreciate all this information and the way you broke it down. I guess you may have already read the question, but it's more a question of how the interfacial stresses are acting, whether they're acting in the horizontal along these fronts that are in the Southern Ocean, and what role the eddies are playing in that interfacial stress.
Right, so they do act in the horizontal along fronts, and you see their importance in the vertical because when you project that into isopignals, even though the two water masses are at the same horizontal level, we like to think of the denser water as deeper, and the denser water often does become deeper. So as you come around a bathymetric feature, you might have a dense water mass that is raised up in the water column, pushing on a lighter water mass right next to each other, picking up, exchanging momentum, and then dropping back down in the vertical. And in this way, that's how we actually, if you look in Drake Passage, where there's no bottom form stress, the interfacial form stress is picking up momentum from the wind, and it's releasing it all the way down in the deepest, the densest of waters. So it works in the horizontal, but because the isopycnals move so much, and that was another thing that really kind of shocked me about when we really started looking at isopycnals in the ocean. This is Antarctic bottom water. This is just a snapshot, but you see Antarctic bottom water in this snapshot up to 1,300 meters. So this isopycnal is changing its depth huge amount. And if you look at the surface density, you will see almost every density class outcrops at some point. Almost every density class runs into the surface at some point. It's very much not a layered ocean in that sense. So it acts horizontally along fronts, but it has a huge manifestation in the vertical in terms of water masses. And the eddies do play a huge role, but it's a completely different story. So what I've really talked about here is the mean interface, the mean bottom form stress, and the mean interfacial form stress. And there's a follow-on paper to Jess Masick's bottom form stress paper strictly about interfacial form stress that gets into much more what the eddies do. And if you look at the time varying signal, it's completely different. When there's a storm that comes through, that momentum doesn't come out along South America. It comes out much more along some of these ridges, and some of the other features. So what's happening in like the time mean view versus what's happening in the transient view is very different. And the eddies are playing a big role in that transient. However, it's really hard to, again, draw strict relationships because the eddies don't correlate, and the eddy interform stress doesn't correlate with the winds because there's so much intrinsic variability. So even though you have a storm, the momentum comes in, it'll do things like form barotropic waves that'll run into land. But when there's increase in winds and then you get an increase in eddies, there's no strict lag lead. It's not clean because there's intrinsic variability. So it's hard to tease out the relationships, but they're there.
Awesome. Thank you so much for your response.
Yeah, and I'm happy to talk more about any of this stuff. I mean, like I said, this was kind of my PhD, and so that was, I don't know how many years ago, but I love this stuff, so happy to talk more about it.
I think Adam had
learning about it.
to leave, so he asked me to be the host. Is there any other questions?
I had one last one. My battery's about to die. I'll try to get it out. I thought it was really cool in your movie of the air-sea flux to see those fluxes, the air-sea fluxes even through the winter sea ice, where presumably there was some divergence in the ice and the surface, sometimes in paleo papers and often in box model world, people will want to seal off the Southern Ocean, not allow air-sea exchange of, say, CO2 to ventilate the deep ocean and the Southern Ocean. Do you see any way that could actually happen in the real ocean?
Well, the ice typically is pretty slushy down there, so there is a lot of leads. We have looked at, I don't know anything about how we should be parameterizing. I can tell you how we are, but we have looked at the Argo floats that go under the ice, and some of them, you just see the oxygen changing all year, just as you would expect from mineralization. Clearly no air-sea exchange. So in some of the floats, it looks like the atmosphere is sealed off all winter. But there are other floats where you don't see that, and you do see times when there must have been an air-sea interaction in the middle of the winter. So I think looking at oxygen in the, that we've been releasing floats down there now for, the oxygen ones first went in 2008, but not under ice. I guess the under ice ones maybe since 2014. So we're building up quite a time series of under ice oxygen floats, and I think they go all the way up to 20 meters before they turn around. So I think you could get a good idea of how often you have it. In the model, the ice typically doesn't 100%. I mean, here you can see in this snapshot, it's 100% closed here, but typically we have like 80%, 90% ice cover out there. There's holes, and so the PCO2 is typically very high under the ice. And so if we say it's 90%, if we say it's 10% blocked, 90% blocked, 10% open, you still get some significant fluxes, as you can tell. If a linear opened up, that would be a really big deal.
But also there's the summer meltback, right? And even maybe I'm outdated on this, but even in glacial times, isn't there still evidence for pretty strong meltback of the sea ice in the summer?
Oh yeah, the ice goes all the way back in the summer, but it leaves a fresh layer usually that helps insulate. The carbon's still there, but it's incredibly diluted by all that fresh water you just dumped into it. So,
you think it wouldn't get out? I think it would get out in the summer. I guess.
I think it's definitely a possibility. I'm not gonna bet that it doesn't. I can show you the Weddell. I think I have the Weddell budget. Oh yeah, here's
that Polinia that just opened up. It had opened up like in the 1970s also.
Yes,
right?
and it was even bigger back then. Yeah. And there was evidence though of pretty deep convection in it this time too. There were not as much as in the 77, 78. But, this is the Weddell-Gyre budget for DIC, and the flux is to the atmosphere in the summer, and it's pretty much negligible in the winter. But the reason why the flux is not much stronger in the summer is because one, you have biological drawdown, and two, you have dilution. And so if you look at just the carbon content in the upper 600 meters appears, this is the carbon concentration. Sorry, this is not the content. This is the carbon concentration. It's very low near the surface in the summer because of the dilution and the bio. And it's very high in the winter because you don't have that, but you have the sea ice blocking it. So I think the length of the season is very important, and these processes need to be understand. This is just from the model. I'm not sure, and I could imagine that it could get out, especially if there's
this is a budget for the whole gyre,
for the whole Weddell-Gyre. Yeah, you can.
Oh, thanks.
This is a paper by Issa Rosa, 2017 probably. And it's an ice concentration. Then Graham McGilchrist has been working on budgets from observations in content, carbon content. But yeah, it's the whole carbon budget. I think we know a lot more about the physical oceanography because floats were released in 2004. And so we have a whole extra decade. The biogeochemical floats released in 2014. I think we'll know a lot more about the carbon budget in 10 years. So it's kind of an exciting time for that. But right now, the carbon budget is lots of questions.
Thank you.
Thanks.
Yeah.
It's getting late. I guess let's thank Matt again. And are you heading out right now, or are you going to take any more questions if anybody wants to chat?
I can stay for another 13 minutes if people want to chat, but I feel like I might, I know I see people in hammocks already. People might want to go relax.
I'm always in the hammock though.
Jealous.
Thank you.
Thank you.